Good evening.
Good evening, ma'am.
Good evening,
ma'am.
Ishan, can you mute everybody, please?
Yeah, sure, ma'am.
That would. Okay. Am I audible?
Yes, ma'am.
Yes, ma'am. Okay, good. Okay.
Yes,
So let's.
ma'am.
Okay, great. Let's get started. So good evening, everyone. And in this session, what I would like to cover is just a brief review of the concepts behind probability, conditional probability, and Bayes theorem. Okay. So the way I have planned this is we'll start by revising the at a conceptual level, and we will look at, I think, one of the common confusions that has been there among a lot of students is about the confusion between disjoint or mutually exclusive and independent events. We'll try and address that as much as possible. Okay. So when I want to start with a notion of statistics at a data science probability, I think the first thing, the assumption is you all are very comfortable with permutation and combination at this point of time. You all know how to count and do all the permutation and combination now, because at the eventually that would help you in trying to see how to manage these things. Okay. So just a second, let me hide this view, and I'm going to minimize this so that I can only see the chat window. 1 second. Okay, yeah, all things done. So let's start. Right. So let me start by again revisiting the basic concept or building block, which I'm going to call a random experiment. So a random experiment is something whereas an experiment is something that produces an outcome. A random experiment is something where the outcome is not predictable with certainty. Now, this is an important point which I want to make, because many a time it is assumed that a random experiment, many times people confuse it by saying that a random experiment is an experiment where the outcome is not known. This is incorrect. A random experiment is an experiment where the outcome is not predictable with certainty. So the most common example of a random experiment is tossing a coin. I know the outcomes are head and tail, but I do not know what eventually is going to come, whether it's going to be a head or tail. So the outcomes are not unknown. The outcomes are known. I know it is going to be either a head or tail, but I do not know what is going to be the actual outcome of the experiment. So this is the first thing which I want to emphasize. That is the difference between a random experiment and an experiment. And why do we need the concept of a random experiment? We need the concept of a random experiment because we want to give a framework wherein we can address the uncertainty that we are experiencing in a lot of day-to-day life. Okay. So once we come up with this definition of a random experiment, the most common thing is we would like to know what is a sample space. So what is a sample space? A sample space is basically the collection of all basic outcomes. So let's start by looking at a few examples of a sample space. So I'm going to second. So are you able to see the OneNote?
Yes, ma'am.
Yeah.
Yes, ma'am.
So the examples of a sample space. So we start by looking at tossing a coin. Okay, so when I toss a coin, just a second. Okay, 1 second. I'm going to toss a coin. When I toss a coin, I can write my sample space as just two outcomes, which is a head and a tail. This is my first example, A. Now, when I toss a coin twice, my sample space is going to be, I could either get a head in my first toss, a head in my second toss, head in my first toss, tail in my second toss, tail in my first toss, head in the second toss, tail in my first toss, tail in the second toss. So you can see that these are all the possible outcomes. So when I'm talking about the possible outcomes, I want to exhaust all the outcomes that are possible. Now let's look at another example where I'm looking at the order of finish in a race. So I have three people. The order of finish in the race could be A could come first, followed by B and C. So the sample space is A is coming first, B is coming second, C is coming third. Or A is first, C is second, B is third. Or B is first, A is second, C is third. Or B first, C second, A is third. Or I could have C, A, B. Or I could have C, B, A. Now, all of you know that this is nothing but 3 factorial, which is 3 into 2. I have 1, 2, 3, 4, 5, 6. So these are the set of all possible outcomes of a random experiment. And this is what we refer to as the sample space of an experiment. Now, let's go to another example wherein I am going to look at the lifetime of a particular bulb. And I can say that that lifetime of a bulb can be written as 0 is less than or equal to x is less than infinity, where x denotes the lifetime of the bulb, and it is all the set of all x such that 0 is less than or equal to x is less than infinity. So you can see that I can define, using all of this, I can define a lot of random experiments, and hence I can define what is the sample space. Okay. So once I talk about a sample space, I said that it should be exhaustive. What I mean by exhaustive is one basic outcome should occur, and mutually exclusive, only one basic outcome can occur. So this is the first notion that you need to understand, is what is a random experiment and what is a sample space. Now, if these concepts are clear, then we go about to introduce the notion of an event in a sample space. Yeah. What is the question, Purnendu?
Yes, yes, ma'am. Actually, I wanted to ask just the mutually exclusive and inclusive. So, what is the basic difference? I mean, what do you mean by probability of an outcome that may come? Means, can you just scroll
Mutually
back to the
exclusive. Yeah, let me look at a. Suppose I'm going to define. I'm tossing a coin. Okay, right? Can I get a head and a tail as an outcome at the same time?
No.
So what it means mutually exclusive is the occurrence of one outcome excludes the occurrence of the or prohibits or bans the occurrence of another outcome. That's why they are called mutually exclusive outcomes. Does that answer your question?
Okay, but what if we toss the coin twice? Then
okay. Yeah. So can I get
Then-
both the heads and both tails at the same time? Here, what is
if-
an outcome? It is a head in the first toss and head in the second toss, right?
Yes.
That is my outcome here. Can I have
Yes.
both the outcomes being head and both the outcomes being tail at the same time?
If we toss the coin twice, then we
Hmm.
can get it.
No. How can you get? Can you get both the heads? That is, the first outcome is a head and the second outcome is a head.
Ma'am, I can't hear you.
Can it happen at the same time?
Ma'am, you weren't audible.
It is not possible, right? How can it be possible? My first outcome being a head, second outcome being a head. That
Hello. Ma'am, you are not audible.
if my first outcome is a head, the first outcome.
Usha ma'am, your
Hello?
voice.
Hello? Am I audible
Yes,
now?
ma'am, you are not audible actually. Means the connection gets disconnected or you got muted or anything like that.
You keep muting yourself. ma'am. It's
No, I'm
your
not
voice
muting
keeps cutting up.
myself. One
Or maybe
second.
ma'am internet issue. You are audible, ma'am.
You are
Am I
audible.
Actually,
now.
ma'am, I think you're audible. Guys, you might want to.
Ma'am, you are
Okay.
audible. You can continue with it.
Okay, right. So the thing is, what we mean by mutual exclusiveness is, see, when you look at tossing a coin twice, the outcome is a head coming in both the tosses. And another outcome is tail coming in both the tosses. So can a head come in both the tosses and tail come in both the tosses? Can I have both these outcomes happening together
No.
simultaneously?
No, ma'am.
That's why I mean by it is mutually exclusive.
Okay.
That is what we mean by mutually exclusive. The outcomes are mutually exclusive. The occurrence of one outcome does
Hmm.
not allow the other outcome. I cannot
Okay.
mutually exclusive. Okay,
So
that is
means
yeah.
So means if we toss two coins together,
Hmm.
then we can say that
Yeah,
we can
when
get.
so whatever is the outcomes, for example, all the examples that we saw here, let me go back and all the examples that I mentioned here, right? Be
Yes.
it the tossing here, okay?
Hmm.
I'm having a race and I'm assuming that only one person can come in each position. If A comes first, can B and C also come first?
No.
So that is mutual. But B is coming first in the third come. But what is the difference? B is coming first, second. So that is excluding C is coming second. So that's why they are called mutually exclusive outcomes.
Okay, ma'am, got it. So it can't happen simultaneously.
It cannot happen. The outcomes are mutually exclusive and they are also called collectively exhaustive. I've listed
Okay.
all possible outcomes. Is that
So
clear?
this will be also true for if we means toss out 3 or 4 coins together.
Anything, it is mutually exclusive outcomes. These are mutually exclusive outcomes. Again, do not get confused between the events. We will be discussing about events very soon. The outcomes are mutually exclusive. I cannot have an outcome happening at the same time. That's what we mean by the basic outcomes. They are mutually exclusive. Only one of them can occur at a time. Is this clear?
Yes.
Okay, right. So now the concept of an event is, now once I have set up this sample space, the next thing which I want to do is to try and explain from the sample space, can I define events? For example, let's look at this example which we have here. In a race, I have 3 people and these are the possible outcomes. Now, I want to define an event where the outcomes or the event where A has come first in the race. What are the outcomes that are related to this event? A is standing first. It's going to be, so I can define an event E1 where A has come first, which will be ABC and ACB. Similarly, an event where B has come first would be BAC and BCA. An event where C has come first would be CAB and CBA. Okay, so these are events. That is a set of outcomes which satisfy a particular condition. And here I have defined the condition to be A has come first, or B has come first, or C has come first. So if you look from a set terminology, events are actually subsets of the sample space. So we are now defined what is an event, because any subset of a sample space, I can define it as an event. Is this clear, please?
Yes, ma'am.
Yeah.
Yes, ma'am.
Yes,
Yes, ma'am.
Okay. So now once I know, Prakar, any questions? Okay.
Ma'am,
Yeah.
am I audible?
Yes.
Can you explain mutually exclusive events using Venn diagram?
Yeah, we are going to do that. Currently, I've just defined an event. I'm going to come and talk to you about what is mutually exclusive events. Okay. We have just defined what is an event. Okay. So an event, what a head appears is just going to be H, an event. So now if I go back to my example of here, whatever I have defined here, now in this, I can define an event. So I have defined all these possible events here. Now, outcomes, all the outcomes are mutually exclusive, but at any point of time, I did not say the events are also need be mutually exclusive. Now let's understand what we mean by mutually exclusive events. Okay. Now suppose I'm going to define an event. Okay. E1, where A has come first, these are the outcomes. The event E2, B has come first, are these are the outcomes. I can also define an A has come first and B has come second. What would that event be? This would be ABC. That is the event where A has come first and B has come second. I can also define an event where A and B occupy the first two positions, where that event is going to be ABC, BAC. Okay. And that's it. So these two are the events where C has come last and A and B occupy the first two positions. So the number of events that you can define are actually the number of subsets you can get from any set. I can also have a null event. Okay, a null event, for example, I can also, what is the chance that there is no outcome? That is 0. So I can define a null event. So actually, I can define as many subsets as they can to make meaningful events. Not all of them need be meaningful, but I can actually define an event as a subset of a sample space. Today's session is precisely to try and clarify your conclusion between mutually exclusive and independent events. Okay. So once we have understood about the events and how we have defined these events, the next thing is to try and give since we are talking about events, I can define all these set operations possible on the events. Now, what are the basic set operations? I can talk about union of events. I can talk about intersection of events. I can talk about complement of events. I repeat, whenever I talk about events, I can talk about union of events. I can talk about intersection, and I can talk about complement. So let's go back and see what is the event for any event E and F. I can define a union of event, E union F, and what would be in this event E union F? It will consist of all the outcomes that are in E or in F or in both E and F. Similarly, E intersection F is going to be E and F. Okay, and null event is a disjoint event. So now let's look at what are mutually exclusive events. So I go back to my thing and I'm going to talk about what are mutually exclusive events. So now, as one of you have requested me, I'm going to talk about, since we all know that a sample space is what is my total set. This is my universal set. Okay, so I represent or the universal set this way. An event is a subset of my sample space. So if I have an event A, so this is a subset of my sample space. So you can imagine in our tossing the heads, my outcomes were HH, HT, TH, and TT. So these are my outcomes. So you can see that this is one outcome, this is the second outcome, this is the third outcome, this is the fourth outcome. Now I can define an event A which says that head in my first toss. So that event is just going to be this set, which is again this set. So similarly, if I define tail in my first toss, that event is going to be this particular set. Okay. Similarly, if I define tail in the second toss, that event is going to be this red. And if I define H in the second toss, that event would be this. So given any sample space, I can define all the events as subsets of my sample space. So far, so good? Yes?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So once I have events defined, okay, second. So once I have my events defined, I can go back to what in my subset. So here I have defined these 4 subsets. So let me go back here and let me look at this event. Okay. Okay, so I said that each one of the. So let me draw this event A, which has the outcomes that my first outcome is a head. And I'm going to define my second, this one, which says that the first outcome is a tail, which is TH and TT. Okay. So I can say that there is nothing common between the set A and B. So I don't have a common thing. Is that clear? Now, whereas if I define my events to be of the following type, I define my events here. Suppose I define my events to be of this kind. A is HH and HD. Okay, the first toss is a head. And I define B to be the event that at least one of the tosses, or the first toss is the second toss is a tail. Then I get these. This is my A and B. So my A is going to have HH, HD. Okay. My B is going to have HD and TT. Okay. So you can see that HD has been an intersection, or it is common between both events A and B. And I can write A intersection B is HD. And the way I can define it is A toss is a head, B is the second toss is a tail. So A intersection B is that outcome where the first toss is a head and second toss is a tail. And I see HD is the only outcome that satisfies this, which is A intersection B. Both I can represent it in my Venn diagram, and I can write it in this way. So what have we seen here is the following, that in this case, I have an intersection. This A and B as events, they are mutually exclusive. In a sense, I know that there is an outcome which can occur, which has a head in the first toss and tail in the second toss. If I have outcomes that are mutually exclusive, for example, when I looked at this event here, okay, when we looked at this event here, the earlier one, which was the following, head in the first toss and tail in the first toss. Okay. Here, when I defined head in the first toss and tail in the first toss, the way I have defined it itself tells that these events cannot have anything, because I cannot have a head and tail occurring in the first toss together or simultaneously. So these events are mutually exclusive, and you can see that their intersection is empty. So I can define what is a mutually exclusive event as the following. I can define the mutually exclusive event. what is this link that is being shared? I think it would be very helpful if we restrict our discussion to only what are the topics that we are going to discuss here. Okay, so that it will not be distracting for others. You can share the links and everything at other forum. Okay, so if the intersection of E intersection F is a null event, which was the case when I defined the event E to be a head in the first toss and event F to be the head in the tail in the first toss, then we say E and F are mutually exclusive events or disjoint events. However, if the intersection is not empty, for example, I could have an event where the head is in the first toss and tail is in the second toss. I could have an event HT. Here, these events were not mutually exclusive. Okay. I'm not sure as to what you mean by mutually inclusive events. I'm not really sure as to what is expected of that, so I'm just going to give it a pass. I will come back to it later. But what? Pardon?
Maybe the mean intersection of two events.
Yeah. So this is the example which I have given. Is suppose I'm defining E to be the event where the head occurs in the first toss, and I'm defining F to be the event where a tail occurs in the second toss. So I can define an event where the head occurs in the first toss and tail occurs in the second toss. This makes meaningful, and there is an outcome which is HT, which is occurring in both the events. So the A intersection B, A and mutually exclusive events. Okay. We'll try our best to solve questions, but this is again at a conceptual lesson. Conceptual level, we are trying to reinforce understanding. So that is the purpose of this session. It is not a problem solving session. Okay. Disjoint and mutually exclusive mean the same. Independent is not this a synonym for mutually exclusive and disjoint. Disjoint and mutually exclusive are the same. Independence is not the equivalent of mutually exclusive. Okay, we'll come to disjoint events very soon. So what we have just introduced till now is the notion of an event, and we say that if two events are disjoint, that is, if their intersection is empty, then they are mutually exclusive or they are disjoint events. Okay, so we can, this is in a Venn diagram, this is the representation of a sample space. I can represent any event as a circle within the rectangle, and you can see that E is an event, F is an event here. So if I have E as an event and F as an event, E union F is the entire shaded region. This blue shaded region is the E intersection F. If E intersection F is empty, as shown in the screen now, I say that E and F are mutually exclusive or disjoint events. Please do not confuse it with independent events here. Similarly, if E is a subset of F, you can see that E is contained in F completely. So these all follow just from our set theory. So once we have just mutually exclusive, we do not have anything called a mutually exclusive. What we know is only collectively exhaustive. What collectively exhaustive means that you are exhausting all possible outcomes. That's what. So when I toss a head coin, the only possible outcomes are head and tail. I don't have any possible outcomes. So sample space is a collection of all collectively exhaustive outcomes. That's all. There is nothing called mutually exhaustive. I have not come across what is mutually exhaustive. So it is collectively, I'm exhausting all possible outcomes. These outcomes are mutually exclusive to each other. And now we have introduced the notion of a mutually exclusive event. Okay. So now the understanding is that you know what is a random experiment, you know what is a sample space. A sample space is the list or it's a set of all possible outcomes, basic outcomes of the experiment, and events are subsets of these experiment. So since I have called the events as subsets, then I can define the basic set operations, which include union, which include intersection and complement. Okay, this is the first understanding. And since I have also represented events and sample space as sets, I can represent these as Venn diagrams for better understanding. So we have introduced these basic concepts. Okay, is this clear, please?
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
So now we
Yes.
move forward to establish the probability axioms. So there are many ways to assign probabilities to the events, because at the end of the day, we are not just interested in listing these outcomes, but we want to assign probabilities to events. So in the lectures, we did talk about the various things. Here, I'm going to go about with the axiomatic approach or the mathematical approach, wherein I again go and say that if I have an experiment whose sample space is S, for every element, I denote a number which is called P of E, and this P of E would lie between 0 or 1. It's basically a function. Okay. So what are the main axioms? For any event, the probability would lie between 0 or 1. In other words, 0 is less than or equal to P of E is less than or equal to 1. The probability of the sample space is 1. This typically, and that's why all this collectively exhaustiveness comes. When I'm talking about a sample space, the probability of the sample space is 1 would mean that I have it at least one of the outcome. There isn't anything that is not going to happen. Okay. Now, the second thing is, for a sequence of mutually exclusive events, the probability of the union is the sum of the probabilities. Now here I have given an union, which is a countable union, but for the purposes of a foundation level course, we are just going to restrict ourselves to a finite union, where I could say that probability of E1 union E2 is probability of E1 plus E2. Now, this is what is referred to as the addition rule of probability. The addition rule of probability states that the chance of E1 or E2 happening, which is what I'm capturing by the union of events, is the sum of probabilities provided they are disjoint. So if E1 and E2 are disjoint, then the probability of E1 union E2 happening is probability of E1 plus probability of E2. So let's go back to our tossing a coin twice. I can define. So if I go back to tossing the coin twice, okay, I have defined A to be HHHT, B to be HTTH. So I know that there are totally 4 outcomes of my sample space, which is HH, HT, TH, TT. What is the probability of A? Probability of A is going to be 1 by 2. Probability of B is going to be 1 by 2. But here I do not have A and B that are disjoint of each other. Whereas here, if I go back to this particular example where I had A and B to be disjoint sets. So this is the example which I had earlier, where A and B are disjoint. Then what describe the event A union B? A was the event that had first toss. B is the event that tail is in the first toss. So A union B can be described as the probability, or A union B is the event where a head can appear in the first toss or tail will appear in the first toss. So you can see A union B is a set of possible outcomes where head is in the first toss, which is HHHT, and tail is in the first toss is THTT. So the probability of A union B is going to be the probability of A plus probability of B. Whereas when I have A and B that are not disjoint, then afterwards I can see that I cannot define probability of A union B is not the sum of the probabilities. So in this case, what we do, what we do is we write this probability as 3 regions. That is what we did. So I can write this as region 1, region 2, and region 3. Now region 1, region 2, and region 3 are disjoint because I have written this. So this horizontal line is my region 1. The vertical line is my region 2. And this slant line is my region 3. I can see that regions 1, 2, and 3 are disjoint of each other. And you can refer to the videos in the class which says that if the sets are or the events are not disjoint, then the addition of probability, that is the probability of A union B, is probability of A plus probability of B minus probability of A intersection B. Now we can verify our addition rule for disjoint events. If the events are disjoint, then A intersection B is null set. Probability of null set is 0, and probability of A union B is just probability of A plus probability of B. So you can see that this addition rule comes from the basic idea of probability of union, which is equal to the sum of probabilities. And if I have non-disjoint sets, I can extend this addition rule to say that if the probability of E1 union E2 is probability of E1 plus probability of E2 minus probability of E1 intersection E2. So as an example, let's look at 2 dice being rolled. We know that this is the set of all possible outcomes. I have 36 outcomes, and in this 36 outcomes, I have 1, 1, 1, 2, 1, 3. So suppose I define A to be the event, that the sum of dice is even. What is the probability of A? You can please use the chat box. If I define A to be the event, that the sum of outcomes is even, what is the probability? How many outcomes satisfy that? What are the outcomes that satisfy? 18. So you can see 1, 1. Then I have 3, 1, 2, 1, 1, 3. So the probability is 18 by 36. Very good. Let me define B to be the first outcome is a 1. B to be the event, the first outcome is a 1. How many outcomes? 6. Very good. Now, does A and B have anything in common? Are A and B disjoint, or do they have anything in common? Is it only 1, 1? What about 1, 3? And what about 1, 5? They are not disjoint events. Very good. Now, let me define another event C, which is saying that the sum of dice, okay, is even. The sum of dice is 6. Sum of dice is 6.
5 by 36, ma'am.
Sum of dice is 6, so it is going to be 5 of those events, which will be 1, 5, 2, 4, 3, 3, 4, 2, and 5, 1. So you can see that the probability of this event C is 5 by 36.
Ma'am, I have a question here, if I can.
Please. Yeah, please.
So this is related to practice assignment that had come earlier, or
can we just postpone the practice assignment, because
No,
I don't
I
have
mean,
the practice assignment.
it's a concept I'm asking, not the question.
Right. At a conceptual level, yes.
Yeah, it's only at a concept level. So the question had stated that if the cards together equal 19, what is the number of events that show that? So here, for example, if you take the addition of the 2 die faces to be 6 or 7 or 8, you're counting both pairs. Let's say 1 and 6 is 7 and 6 and 1 is 7.
Yes.
But in that question, it was very specifically stated that 10 and 9 and 9 and 10 are the same event, and so they will not be counted twice. And that was very confusing.
Yeah, it depends on how you're defining an experiment. Okay.
Okay.
Now let me tell you, here the experiment is very clear. I'm rolling a dice twice. And how am I listing my outcomes? I'm listing my outcome as what is the outcome on my first roll and what is the outcome on my second roll. Okay. So 1, 6 is different from 6, 1.
That's right.
Right. So it all depends on how you're defining what is your outcome. So here you can see that 1, 6 and 6, 1 are very different from each other. Because it is whereas when I am counting an outcome 4, 4, it would mean that the outcomes on the first and the second dice are the same. So I have a 1, 1, 2, 2, 3, 3, etc. Does it answer your question?
Well, actually, that was the.
So you need to go back. I do not have what is this one. You need to go back and see what is the experiment outcomes and how you're capturing the outcomes.
Okay, so the
Yeah.
experiment was that the two cards are drawn from a deck. What is
Exactly.
the
So
probability?
you should see whether it is, so whether the experiment said whether it's a drawing with replacement, without replacement, all of that you need to understand. Okay. So in the interest of time, going forward, we can have a one-on-one, or you can send me an email if there is a doubt. Of course, mark your instructors to that. Okay.
Sure, ma'am.
Right. Okay. So this, so what would be A intersection B? Remember, I defined A to be the event where the sum of dice is even, and B is when the first roll is a 1. So what would A intersection B be? You can send an email to your course instructors, and if need be, they will contact me always. Okay. So what is A intersection B? We said that A intersection B is already there, right? What would A intersection be in that case? A is the event, sum of dice is even, and B is the event. My first one is a roll is a 1. I'm not asking the probability. I just want you to give me what are the outcomes here. A intersection B would be a 1, 2. No, sorry, a 1, 3, a 1, 1, a 1, 5, right? So you can see that from here, you can see the reason why we are going back is immediately okay, I think Ishan and Prashant, you can take care of this email of our instructor and everything. I'm just going to focus on
we will look into it.
Yeah. Thank you. Okay. So you can see that the minute I have defined events as subsets of this set S, I can define all the events. I can define all A, B, C as subsets. I can define the complement. So what is B complement? If I define where I define the event B to be the event that the first roll is a 1 or the first outcome is a 1. What is B complement? Just describe it. I don't want you to give me a number or anything. It would be the first outcome. So all the other things, which is from 2, 1 to 6, 6, all the first events. Okay. So get into the habit of describing events rather than jumping straight into finding what is the probability. Here also you can see that even before I asked what is the probability, there was an urgency to give the probability. The first thing is we need to describe the event. Yeah, it is not hard. It requires a practice. It is not hard. Okay. So the reason why I want you all to start describing events is only then would you appreciate the need for finding probability, and it does not become a routine rote mathematical exercise. Okay. Because at the end of the day, as analysts, you guys are going to define events and you need to get probabilities of events. Okay. So it is not going to be a mathematical problem solving exercise. So that is the reason why I'm telling you to describe events. For example, what would be the event A or B intersection C? Remember, B was the event where my first roll was a 1 and C was an event where the sum of dice was equal to 5. So if I want to define an event which is B intersection C, the way I would describe it is the first roll is a die and the sum of the outcomes add up to 6. I have only one outcome. Okay. Sum should add up to 6. So the only one outcome that satisfies this is 1, 5. So get into the practice of describing events. You will get understanding. That's what I want you to focus on. Just try and start getting into description of events. Okay. Once you describe events, then afterwards you can see that what is A intersection B intersection C now. Remember, A intersection C is this one single outcome 1, 5. B was the event where your first die is so sum of dice is even, and the first roll is a die 1, and it's sum equals 6. I see there is only one outcome, which is 1, 5. Okay, so that is what I just want you all to try and see is start describing events. Now, once I describe the events, then afterwards I can, I cannot write all the events here. Okay, so you can describe events and try and get all events here. So now first you can try and see that given these events, we can actually try with the probabilities associated with this event. Yes, Purnendu.
Ma'am, is it always that we have to describe the sample space or create the sample space?
See, that would help you, but most of the time, see, the reason is, let me give you an analogy. Now, if you want to learn to drive a car or a bike, okay, there are various ways to do it. You can just go and you can hit yourself against a lamppost. You realize something has happened, and then afterwards you come back and you can learn to do it. Okay. But if somebody tells, okay, you get into the car, you wear your seat belt, you put your gear in neutral, and then you start shifting your gears. These are the structured way to help you learn to drive a car. Is that right?
Yes.
So here what we are trying to give you is a structured way to understand how probabilities of events can be given. So once you master this, then at a point of time, you don't have to write the sample space and everything. It will become very clear to you, okay, this might be the probability, because most of the time probability would be very subjective in nature.
Okay, ma'am.
Right. So that, but however, if you want to understand this, you need to understand these are, that's why I say what we refer to as building blocks and probability. Okay.
Yes.
You can see that this would help you understand. For example, if you're asking, so you need this to understand how to define your random variables. You need this to understand how you are going to raise questions that can be converted into random variables, right? Without an understanding of this, you cannot understand what is a random variable.
Yes, that's used exclusively.
Okay, so you need to have an understanding here. Is it clear?
Got it, ma'am.
Yeah, right. So this understanding will help you, because at the end of the day, a random variable is assigning again a value to every outcome of the sample space. It is a function which assigns a value to every outcome in the sample space. If you do not know what is the sample space, how would you go and define a random variable? And you need the concept of a random variable, because eventually your modeling is everything is going to depend on how you define these random variables. Okay. So this is, again, I keep reiterating, have a very strong foundation. If you have a strong foundation, everything else will fall in place. Okay. Right. So now let me explain the important concepts, okay, in the following way. So suppose I have two events E and F and another two events G and H. Okay. Now the row, this is what is given in blocks here. So what is given as A is the number of outcomes in E and in G, which is A. Similarly, E and H is B. So the total row total here is A plus B. The row total here is C plus D. The total number of outcomes is A plus B plus C plus D, which you can see that is equal to capital N. So if I want to know what is the probability of E intersection with G, that is pretty simple. That is just A divided by N. Probability of E intersection H is again B divided by N. Probability of F intersection G is C divided by N. F intersection H is D divided by N. Now, suppose I want to ask what is the probability of E? What would be the probability of E? How many outcomes correspond to E? That is the row total. And from the row total, I can see that that is nothing but A plus B. So the probability of E is going to be A plus B divided by N. The column total, again, probability of G is going to be A plus C divided by N. So row total by total number of outcomes. Similarly, column totals by total number of outcomes, which is A by, so E is going to be A plus B by capital N. F is C plus D by capital N. Column total probability of G is A plus C by capital N. And H is B plus D by capital N. Now the question of conditional probability. We are going to understand the notion of conditional probability using this table. Yes, Ritik.
Ma'am, E and G union E and H, it is A plus B, but how it can be probability of E? Means there can be other events?
No, E, how many outcomes? So what is given here is there are totally N outcomes. Okay.
Okay.
What is this A telling me? It is the number of outcomes where both E and G have occurred together.
Okay,
Right.
but there could be other outcomes which are neither in G and neither in H, but are in E.
I don't have any. This is the only thing which I have given you. There are no other outcomes. This is exhaustive. Okay.
Okay.
This is exhaustive, and from this exhaustive list, I'm trying to come. There are no more outcomes. Okay. Right. In that case, it is going to, I agree with you. If there are other outcomes, then I should have had another column. But here I have A plus C, which is equal to N. Right. So there are no more outcomes. Right. So what I can see is now, given E, what is the total number of outcomes in E? It is A plus B. How many belong to, say, if you recall, this is something very similar to the relative frequency that was introduced in the week 2 or week 3, I don't remember. Okay, in the descriptive statistics thing. So given, so this is given E. I have A plus B, which is the total number of outcomes that satisfy E. Of this, how? So what is the probability of this event G happening given E has happened? So I'm conditioning. I want you all to condition it on E. So if I condition it on E, it is given E. So what is this given E? How many events are there in E? It is A plus B. So this probability of G given E is going to be A divided by A plus B. Is that understanding clear? Similarly, what is the probability of F given H? F given H. What is the, yes, it is D by B plus D. F is F given H, this entire thing is B plus D. So F given H, so I can possible conditional probabilities, okay, which is E given H. So you can see that E given G is A plus C. Okay, F given G is C by A plus B. G given E is A by A plus B. H given B plus B. So the notion of conditional probability is, I know some event has happened. Given that event has happened, can I comment on the probability of another event happening? Now, for example, if I toss a coin twice, okay, what is the chance that I will get a head in the first toss?
1 by 2.
It is 1 by 2. What is the chance of me getting a head in the second toss? 1 by 2 again?
1 by 2.
What is the chance of me getting a head in the second toss with the information I give you is there was a head in the first toss? It's the same.
Yes,
So in other words, the conditional probability of getting a head in the second toss, given the information that there was a head in the first toss, is the same as the unconditional probability of getting a second toss. Is this clear? I repeat, listen to it carefully. The conditional probability of getting a head in the second toss given the information that there was a head in the first toss, is the same as the unconditional probability of getting a head in the second toss. Would you all agree with the statement?
Yes, ma'am.
Yeah. So this is what referred to as a conditional probability. So I can say that the event of getting a head in the second toss is independent of the event of getting a head in the first toss.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, Prakar? Answer. Yes, Prakar.
Ma'am, conditional probability for mutually exclusive events will be 0.
Let's come to that. Let's understand first of all what is conditional probability. We'll come to it very. See, the thing is, I want to tell you what is a conditional probability first. I'll come to conditional probability. I have not defined anything, but just now I'm just talking about what is the conditional probability of events. I'm just defining what is the conditional probability. Okay. So now let's go back to this example here. Okay. Let me define an event A, which says that the first throw results in a 4. Just listen to these events, okay? The first throw results in a 4. And my second event says that the sum of the throws is a 10. Is this clear? Okay. Now, let's look at the second event, which is the sum of the events is a 10. When can a 10 occur? When can the sum of events be a 10?
4, 6.
4, 6. Forget about the first toss thing. When can a first sum of events be a 10? What are all the outcomes that give the sum of events is a 10?
4, 6,
4, 6, 6,
5,
4,
5.
5, 5.
Very good. Okay. So can I get a sum of 10 independent of whatever was my first throw? Or does it depend on what was the first throw? It depends. Okay. So now I said.
Completely.
Pardon?
Not completely, ma'am.
What do we mean by not completely? There is no.
One of the event will cover up out of that.
No, but it depends, right? To get a sum of 10, I cannot get a sum of 10, whatever was my first event. Can I? Or does it depend on what was my first throw? Right. Now let me define as event C, which is the sum with throw, okay, was a 4, and the sum of events is a 7. Now, sum of events is a 7. Can I get a sum of 7 irrespective of whatever was my first throw?
Yes, ma'am.
But I cannot get a sum of 10.
Yes, ma'am.
Yes,
Right.
ma'am.
Yes, ma'am.
Is this idea clear? So when I defined an event which was sum of 7, I saw that the sum of 7, getting a 7 is independent of what was my first throw. Okay. It will always be there, right? A minimum 1 should be there, or 2. With a 1, I know it is a 1, 6. With a 2, I know it is a 2, 5. A sum of 7 can independent of what was my first throw. Whereas a sum of 10, what about a sum of 8? Does that depend on what was my first throw, or is it independent of what was my first throw?
Depends.
So now, when I ask you questions of this kind, you understand when it is dependent and when it is independent, right? So now let's try a notion. Is it clear?
Yes, ma'am.
Yes, ma'am.
Okay. Is this clear? Right. So now let's look at the example that we have just spoken about. I have my sample space given here. Okay. And my sample space was a 1, 1, 1, 2.
I have a question, sorry.
Yeah.
Ma'am, so basically we are saying that whenever the sum will be more than the least number and the maximum number.
I'm not telling anything of that kind. It is just based on intuition, and I want to create a theory here. That's it. Okay. We are not, see, let's not complicate our lives at all. Okay, I'm not telling about least number and highest number. I'll go back to this. If you look at this rolling a dice twice, I have defined two events. Okay, the first event I defined was the first row is a 4. The second event, so let me call that an event A. Okay, what are the possible outcomes in that event? The possible outcomes of that event where my first row is a 4 is 4, 1, 4, 2, up to 4, 6. Is that right? Yeah.
Yes.
Then
Yes,
I'm
ma'am.
defining this event B that the sum of my outcomes is a 10. What are the possible events here? This is a 5, 5, a 4, 6, and a 6, 4. Right? I'm defining another event C, which is the sum of outcomes is a 7. I have here 1, 6. I have 2, 5. I have 3, 4. I have 4, 3. I have 5, 1. And I have a 6, 1. 5, 2 and a 6, 1. Right? Is that right?
Yes, ma'am.
Okay. Now the question I'm asking is, without even going to the set logic and everything, I asked that, can I get a set of 7 irrespective of what was my first outcome?
Yes, ma'am. Yes, ma'am.
Can I get a sum of 10 irrespective of what was my first outcome?
No,
No, ma'am.
No. So, and how did I define my event A? I picked them. Agreed? What was the first outcome in event A? I fixed it, right? I said the first outcome is 4. Okay. So I want to know what is the chance of B conditioned on A. That is, what is B? B is saying that the sum is 10. Okay. So I'm asking you, what is the chance of a sum being 10 given that the first outcome was a 4? What is the chance of that happening?
1 by 6.
1 by 6.
1 by
Probability of
6.
that is 1 by
6.
1 by 6. All of you agree?
Yes, ma'am.
Okay. Now, what is the chance of B happening? 3 by 36.
Yes, ma'am.
What is the chance of A happening? 6 by
6
36.
by 36.
Okay. Do I have an intersection?
Yes.
Yes, ma'am.
Yes,
What
ma'am.
is the
Yes, ma'am.
intersection?
4, 6.
4, 6.
That is 4, 6. So what is the chance of that happening?
1 by 36.
1 by
1 upon
36.
36.
Very good. Okay. Is it clear? Okay. So by the definition of conditional probability, I know the chance of B happening given A happens is defined to be the probability of A intersection B divided by probability of A. Let's understand how we have got this at all. Okay. How have we got this? Now again, okay. This is my event A. This is my event B. Okay. Now, given A has happened, chance of B happening is going to be the following. I have this is the area common to this A intersection B. Is that right?
Yes,
Okay.
ma'am.
Yes, ma'am.
So this shaded region divided by this total area is the area, is the probability. This is the probability of B happening given happened, right? This is the shaded region. This is the total region. So what is the probability of B happening in this? It is the shaded region, which is the probability of A intersection B divided by this total probability, which is probability of A. It's a fraction. What is a fraction of the shaded region? And this is what we define as probability of B given A. That is what is a conditional probability. So what is a conditional probability in this case? What has been my conditional probability? I know probability of A intersection B is 1 by 36. What is the probability of A? 6 by 36. So what is probability of B given A? It is 1 by 6.
1 by 6.
And that is what you have given earlier, even without knowing the formula. Is that clear? Now do the same thing with C. What is the probability of C? What is the probability of C?
6 by 36.
Okay, what is the probability of C intersection A? Does C and A have anything in common?
1 by 36.
4 by 4 3.
4,
3. Okay, so what is the probability of C? Intersection
1
A?
by 30, 1 by 1 by 36.
1 by 36. 1 by?
1 by
What is the
6.
pro-
1 by 6.
probability of A?
1 by 6.
What is the probability of C?
1 by
6
6.
by 36.
6 by 36.
Okay. So, one second. So if you look at this, when I'm looking at the sum of 7, one second, I lost this. Okay, so I have a probability of C given A. Okay, right. This is my conditional probability statement. Okay, now, was C independent of A or was it dependent on A?
Independent.
Dependent on A.
C. Getting a sum of 7, did it depend on whether my first was a 4 or was it independent of whether it was a 4?
Independent. Independent of A.
Right. So here you can see that probability of C is, so what is my probability of C?
6 by 36.
6 by 36.
Which is 1 by 6. What is probability of C given A?
1 by 6.
1 by 6. So probability of C given A was the same as probability of C?
Yes, ma'am.
Yes, ma'am.
So that's why it is independent.
Yeah. Probability of B given A, what was that?
1 by
1 by
6.
6.
1
What
by
was
6.
probability of B?
3 by 36.
3 by 30.
So you can see that the conditional probability of B given A is not the same as the unconditional probability. So B depended on A, whereas the probability of C given conditional probability. So C was independent of A. Is that clear?
Yes, ma'am. Yes.
So
Yeah,
when
ma'am.
yeah. Any questions?
Got the intuition behind that.
Pardon?
Got the idea, ma'am.
So this is, so when I have, is this clear to everyone? Okay, so when do I say two events are independent of each other? I say two events are independent of each other if the conditional, so see, understand what is this conditional probability. A conditioned on B, if it is the same, suppose B has no effect on A. Okay, then B and A are independent of each other. Would you agree or not?
Yes, ma'am.
Yeah, ma'am.
Yes,
Right.
ma'am. Yes, ma'am. Yes, ma'am. Yes, ma'am.
Right. So now what does the multiplication rule say? The multiplication rule. So if I look at this and cross multiply, probability of A intersection B is probability of A conditioned on B into probability of B just by cross multiplication. Yeah. But
Yes,
if
yes.
A
Yes, ma'am.
and B
Yes,
are,
ma'am.
Yes, ma'am.
if A and B are independent of each other, then what is probability of A conditioned on B? A is independent of B. So what can you say about the conditional probability of A given B?
It's 1.
Not 1.
PA.
It is
Probability of A.
probability of A. A does not. It is not
P
zero.
of A.
No. It's nothing of zero. Don't get confused with the disjoint. Just look at if A is independent of B, what is probability of A conditioned on B? It would be probability of A
Probability
only,
of
right?
A.
It is a PA, ma'am.
So what would be probability of A intersection B? It would be probability of A into probability of B.
Yes, Yes, ma'am. ma'am.
Yes, ma'am.
Yes, ma'am.
So the whole moral of the story is when I'm talking about union of events, when I have two disjoint events, the probability of the union is sum of the probabilities. When I have two independent events, the probability of the intersection is the product of the probabilities. That is product of probability of A into probability of B. So E is independent of F if probability of E intersection F is equal to probability of F into probability of E. Is this clear?
Yes.
Yes, ma'am.
Yes, ma'am.
Rajalakshmi, what is it?
Ma'am, does the converse also hold true? Like independent?
Yes, the converse holds true for only two events. So two events, so you can see that is the thing which I am displaying on the screen is two events are independent. This is only for two events, okay? Two events are independent if and only if the probability that both of them are equals to the product of the individual product. This is true. The converse, this is an if and only statement for two events. That is
Regarding disjoint for disjoint events?
What do you mean by disjoint events? This is only
for disjoint events, we have studied that the probability of their union is equal to sum of probabilities, right?
Yes.
Does the converse hold true for any number of events there?
What would be the converse? Can you just state what is the converse in that case?
Union is equal to sum of their probabilities means the events are disjoint. Like disjoint means addition rule applies. Addition rule applies implies disjoint. That is what I'm saying. Two statements.
But so that is the thing, na? If addition rule, if the intersection is 0, then the probability of the addition P of A plus P of B should be equal to that.
Okay, if there is a third event, if there is a third event, I'm saying even then P of A union B union C will be P of A plus B plus C. That would hold true, right, for disjoint.
So, okay, so what you're saying is the following. If I understand the question right, just a second. So I have a sample space here. You're saying I have A and B disjoint. Okay.
C also A, B, C, 3 are disjoint. So the sum will be so the union will probability of union will be sum of their individual probabilities.
Agreed. Yeah.
So just like how we are limiting to two events in the case of independent, the previous
in case of independence, this if and only if statement, that is probability of A intersection B equal to probability of A into probability of B. Okay. This is if only if holds only for two events. When I have more than two events, then I look at what we refer to as pairwise independence. So you can see this. Three events are said to be independent if the probability of the intersection has to be the product of the probabilities. In addition to that, I want the pairwise independence to also be there.
Yes.
Does that answer your question?
Yes, ma'am. Thank you.
Yeah. So I have, in addition to this first condition alone is not sufficient. That's what I want to say.
Yes, ma'am.
Okay. I need pairwise independence, and by pairwise independence, I say that E intersection F should be also. So it is not that probability of E intersection F intersection G should be. So this makes more sense in independence, right? Whereas in union, it was just addition, right? Okay. So here I say that it is probability of E intersection F intersection G should be the product of probabilities. In addition, every pair, how many pairs do I have when I have three events? It will be 3C2. So I have three pairs, right? E intersection F, E intersection G, and E F intersection G. Does this answer your question? Yeah?
Yes, ma'am. Yes, ma'am.
Yeah. Is this clear? Now, the major problem is and disjointness. See, disjoint and independence, for example, when I have two events, okay, when the outcomes, so these events have no outcomes in common, I say they are disjoint events. When occurrence of one does not impact the occurrence of another event, I say they are independent. So the mutually exclusive and independent events should not be confused with each other. Is this clear, please?
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
Yeah. So this is the first thing which we wanted to address is the law. So now let's do a simple problem. Just an example.
Ma'am, sorry, I had one question. If I
Yeah, please. Yeah, go ahead.
So for independence events, the union function can be defined similar to the same way we do for disjoint. It is A union.
See, you can define union, complement, and this one intersection for any set of events. They are just subsets. Only thing they should be meaningful.
Okay. So we just use P of A plus P of B.
See, for example, you said that the occurrence. Let's go back to our dice problem itself, right? Okay. I know C and A here are independent of each other. This is what we have just established. Yes or no?
Yes, ma'am.
Now describe the event A union C. Describe the event A union C. Hello? Describe the event A union C.
Yes, ma'am. 4126 162534
No,
54.
describe it, not in terms of outcomes. Describe it. Just please mute yourselves if you are not telling something related to the course, please. See, A is the event which had the, see, I described the event. I did not specify the outcomes. When I described A, I said A is the event where the first throw is a 4. C is the event where the sum of throws is a 7. So describe A union C here.
The first throw is a 4 or
the sum is a
7.
How difficult was that? So I can describe this. So I have described an A union C here, even though A and C are independent events. Is that clear?
Yes.
Can we describe A union B?
Yes, yes.
What is A union B now? The first throw is a 4 and the sum is 10.
The sum is 10.
Now describe B intersection.
Yeah.
B union C.
B union C.
If the first is 10 or the second.
Sum is 10
The sum is 10
7.
or the sum is 7.
B
Either 10 or
intersection C.
7.
B intersection C.
The sum is 10 and
Sum is 10 and sum is 7.
Can that happen?
No.
ma'am.
No.
So what is that kind of? It's a null set, right?
Yes, ma'am.
How do you get it? So I have defined all the possible events. What is the complement of C?
All other event is not.
Event which not sum is not 7.
Ma'am, when sum is not 7?
Yeah, that's it. So now are you getting a hang of it? So I could see, it is not that I cannot define probabilities or union. Or, I have defined all the example. Yes or no?
Yes,
We
ma'am.
have defined
Yes,
intersection.
ma'am.
We have defined
Yes, ma'am.
union. We have defined this one, and we have described it. So again, I reiterate, the minute you all start describing the events, it will start making more meaning for you. You will start understanding it. One thing is, you will always get confused if you start applying formula. Understand the formula and then start applying it. You will understand what is happening. Is this clear?
Yes, ma'am. Yes, ma'am.
Yes.
Yes, ma'am.
Right? So then, if this is clear, let's do a small example to reinforce the concepts that we have learned so far. Okay, the concepts that we have learned so far. Just a second. I'll go back here. Yeah. So now let me give you this one. There are 4 women and 6 men. I'm choosing 2 people randomly from this set. What is my sample space? I repeat, there are 4 women and 6 men. I'm choosing 2 people randomly from this set. What is my sample space?
10C2, ma'am.
Pardon?
Yes,
10C2.
Yeah.
ma'am.
So how many will
Yes,
I have? 10C2 is
45.
10C.
10C2. What is it?
45, ma'am.
45, ma'am.
So what are the possible things?
45, ma'am. 45. Just
No,
45.
the order in which I'm picking it up is also important. So how many ways can I do that? So imagine I'm selecting a president and a vice
10C2,
president.
ma'am.
I'm selecting a president and a vice president. Okay. So what now? What would be the total outcomes in my
90, ma'am.
90.
90, ma'am.
All of you agree? Okay.
Yes, ma'am.
Ma'am.
Professor, good? Very good. Now let me define my first event. Okay, I'm going to describe my event here. Okay, listen to it carefully. My first event is that the president is a woman. How many outcomes do I have? The president is a woman. President is a woman.
4C1, ma'am.
How many ways can that happen? Only 4 ways a president can be a woman.
Yes, ma'am.
Yes,
Either the
ma'am.
first person is a woman, or the second person is a woman, or the third person is a woman, or the fourth person is a woman, right?
Yes.
Yes, ma'am.
Yes, ma'am.
You can verify the formula later. I just want you to think about it. Okay. Right. Now is that the vice president is a woman.
Ma'am, you are not properly audible.
My second event is, my first event is the president is a woman. Okay. Right. How many ways can that be?
ma'am.
How many possible outcomes do I have for that? President is a woman.
Yeah,
4
four,
ways. Right?
four.
4 ways.
Right. Now the second event I'm defining a woman. Again, how many ways can that happen?
4 ways again.
Okay. Now I ask you, is there a chance that both the president and the vice president is a woman?
Yes, there
Yes,
can
ma'am.
be.
Yes, ma'am. Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Okay. Now I'm going to ask you whether the vice president can be a woman, given that there's the chance that the vice president is a woman. Does it depend on whether the president was a woman?
No, ma'am. No, ma'am.
No, ma'am.
So I want you all to verify this now. Now you all have, without any math involved,
Yes, ma'am.
right?
The probability of
You do that. I just want, describe the problem to you. Now it is for you to, now you can say questions you can ask. What is the chance that, so this is an application actually? Yes or no?
Yes, ma'am.
From 4
Yes, ma'am.
people and 6 people, I'm just asking you. Now, how would you, this one, whether the event that the second person, vice president is also a woman, depends on whether the first person is a woman or not. All these are the questions that you want to ask, and just verify the probability. See whether your intuition and the probability results are the same. Is the question clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay, tell me, what is the chance that the first person was a, what is the chance of for president being a woman?
4/10.
4 by
4 by 10.
Very good. Right, 4 by 10. What is the chance that what is the chance of the second person, of the vice president being a woman, given that the first president is a woman?
3 by 10.
3 by 10.
3 by 10.
No.
Oh, sorry. 3
Will it be 3 by 10?
No, no, ma'am.
No, ma'am.
It will not
Ma'am,
be
it's
3 by
3/9.
3
3 by 9. 3 by 9.
3 by 9.
3/9.
Or it is given. So how many women are left?
If
Three
president is
women.
already a
Three.
woman, how many women are left?
Nine.
Three,
Nine.
right?
Nine.
Three women are
One
left.
of
Three.
them. So it will be 1 by 3, right? Is that clear?
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Is it clear? So that is how you should try. So again and again, what I'm trying to tell you is, don't always be under this one to apply a formula and get things. First, understand what is happening, then applying the formula will come. I hope I have been able to convince you about that. Okay. Application and understanding formula is very, very important. I'm not even debating that. But try and understand the problem, internalize the problem, then it will become easier for you to apply. Is that clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. So now the next thing which I was supposed to do is the second. Yeah, I think the next thing was conditional probability has been done. Independent events are done. Okay. Base theorem. Okay. Right. So let me go to the next one. It's the law of total probability. Okay. So again, this is a very, very important law which we are going to refer to as the law of total probability. Now, what is the law of total probability? Again, I have my sample space here. Okay. Imagine I am dividing the sample space into two events, which is A. And what would be this event? If this event is A, this entire rectangle is A, what would this event be?
A
complement. A complement.
Very good. Okay. So this could be this could be the event of rain, and this could be the event of no rain. These are complementary, right? Rain
Yes,
and no
ma'am.
rain. Okay.
Yes, ma'am.
Now I have a event here, which could be the probability of a match happening. Okay, or India winning or something of that kind. Okay. Now this could happen if there's a rain and if there is no rain. Agreed? Or probability of some event, some sale happening or an exhibition happening or a successful sale happening or something. Okay. So I can have that probability of this event. Let me call this event B. I can cut this probability of B to be these two regions. So this event B can happen even if it rains and if it does not rain. Can I cut this region into these two events? What is region in terms of B and A?
B intersection A.
Very good. And what is this region?
B intersection A
B
complement.
intersection A complement.
Intersection A complement.
So would you all agree that I can write B as B intersection A union B intersection A complement?
Yes, ma'am.
Yes, ma'am.
Yes,
And
ma'am.
are these two sets disjoint? That is the vertical line, the horizontal lines, are they disjoint?
Yes.
Yes,
So if they are
ma'am.
Yes, ma'am.
disjoint, then I can apply my additional rule and I can get this as probability of B intersection A plus probability of B intersection A complement. Can I write it in this way?
Yes, ma'am.
Yes, ma'am.
Now again,
Yes,
Yes,
ma'am.
ma'am.
I go
Yes.
back to my definition. I know B intersection A is B conditioned on A into probability of A. This is my definition, right? Similarly, this is probability of B conditioned on A complement into probability of A complement. Is that right? So I can express this probability of B as probability of B conditioned on A into probability of A plus probability of B conditioned on A complement into probability of A complement. Now suppose I have, so where do I apply this? Suppose there is A is the event of rain happening. A complement is the event of no rain happening. And I tell you the chance of a successful sale, if it rains, is say 0.3. Successful sale, if it does not rain, is 0.6. Okay. I repeat, I say the chance that you have a successful sale, if it rains, is 0.3. The probability of if it does not rain is 0.6. Obviously, the probability is higher. The chance that it rains is 0.2. The chance it does not rain is 0.8. What is the probability of successful sale? Is the question clear?
Yes, ma'am.
Yes, ma'am.
The probability of a successful sale, if it rains, is 0.3. The probability of a successful sale, if it does not rain, is 0.6. Okay. The chance that it rains is 0.2. The chance it does not rain is 0.8. What is the probability of a successful sale? So what is your probabilities here? So I want to know the probability of a successful sale, which I can write as probability of a successful sale given it rains into probability it rains, plus probability of a successful sale given it does not rain into probability it does not rain. Would you all agree? What is the probability
Yes,
that
ma'am.
of a successful
ma'am.
sale given it rains?
0.3, ma'am.
0.3.
What is the chance it rains?
0.2.
0.2.
That's the 0.3 into 0.2. What is the probability of a successful sale given it does not rain?
0.6, ma'am.
0.6.
What is the chance it does not rain?
0.8.
0.8. Going to be the probability of a successful sale. Is that clear?
Yes, ma'am. Yes, ma'am.
Okay.
Yes, ma'am.
Now let me give you another example. Okay. So now I have a company. Second. Now let me discuss another example. Okay. I have a company for which materials come or products come from 3 places. Let me call it from A, from B, and from C. Okay. 30% comes from A, 30% comes from B, and 40% comes from C. So far, so good. I have a company which receives products from A, B, and C. How many products come from A?
30%.
30%.
So what is, so I pick up any product, what is the chance it has come from B?
30%.
30%.
30%.
It is 0.3, right? What is the chance it has come from C?
0.4.
You all agree that I write this as point A equal to probability of A is 0.3. Probability of picking up any product, it is 0.3. Probability of C is 0.4. Is that clear?
Yes, ma'am.
Now
Yes,
I
ma'am.
am going to talk about a set, which is the set of defectives. Okay. What would this portion represent? You describe this portion.
A product is A intersection
from
A
A
and
and
defective.
This is a product is defective and comes from A.
Comes
This is
from
going to be product comes from B. This is a product that is a defective and comes from C. Right?
Yes, ma'am.
Okay. Now I'm further telling you the chance of finding a defective if it comes from A is say 2%. Okay. Chance of finding a defective if it comes from B is say 1%. And chance of finding a defective given it comes from C is 3%. Is this clear?
Yes, ma'am.
What is
Yes,
the
ma'am.
probability? I then mix up all of them together. I pick up an element. What is the chance that this would be a defective element? By applying law of total probability. Probability of a defective.
It is defective and comes from A, or defective
Very
and
good.
comes from
So that
B.
is defective. It comes from A into probability of A
Yes, ma'am.
Yes, ma'am.
plus probability
Plus
of defective and comes
from B
to probability of B.
into probability of B.
Plus
Right.
probability of coming from C and defective
Very good. This is precisely
into
what is that law.
CC.
What is this? This is 2.02 into 0.3. Right? What is this? This is 0.2%, right? And this is 30%. So what is this probability? It will be 0.02 into 0.3. Agreed?
Yes, ma'am.
Yes, ma'am.
Similarly, this would be 0.01 into 0.3. This would be 0.03 into 0.4. Is that clear?
Yes, got it.
Yes, ma'am.
Got it? Right. Now, I I mix all my products, I pick up one product. Okay. I see that it is defective. I want to know what is the chance it comes from A. So how would I express this as a probability? What is the information that you have given now? What do you know now?
We know it is coming from
Product is defective.
I know that I want
Product
to
is defective. is
chance
given.
it came from A. I know it is defective. I want to know the chance it comes from A. This is what I want to know, right? Agreed?
Yes. Yes. Yes.
Yes,
Given
ma'am.
the information that is given to you, it is defective. I want to know what is the chance it came from A. Now, what would this be? This would be probability A intersection D divided by probability D. This is what is my conditional probability problem.
Yes.
Yeah? Now I can
Yes,
write
ma'am.
this as probability of D given A into probability of A. And I already know what is this probability of D, right? This is what we refer to as the Bayes theorem. Okay, so this is the law of total probability. Now, what is Bayes theorem? Now, this, whatever has happened before, right? That is this E given F1, probability of F1, probability of F2, probability of Fk, or what were my prior probabilities. Okay. Now, this probability of F5 given E is what I refer to as my posterior probability. Is that clear?
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
Okay, so this is what
Ma'am,
is
if you
called as-
don't, ma'am, if you don't mind, can you go back to the formula you had written, please? 1 second.
This one?
Yes, ma'am. Just
1 second.
So in the numerator, when you wrote A intersection D.
Let me write it again. So I want to know probability of A given D. What does this mean? I see a this one is defective. I know what I want to know. What is the chance that it came from A? Okay. Now you can look at this. You can have various versions of this. Okay. For example, this could be that there are 3 colleges, A, B, and C. Okay. And this could be the number of people who have cleared. Imagine. Okay. Instead of defective, it could be the number of people who have cleared JEE. So what would this portion be? This would be the number of people from college A and who have cleared JEE. Is that clear?
Yes.
This would be the number of people who have from college B and cleared JEE. Now I randomly pick up a student. I find that student JEE. Okay. Now I want to know what is the chance that he comes from college A. That is what this would mean. Is it clear?
Yes, ma'am.
You can apply this to a lot of situations.
But you wrote P A intersection D and then what? And then what?
Divided by probability of D. See, what is my conditional probability definition? Probability of A given D is probability of A intersection D divided by probability D. This is my conditional probability.
Yes.
Sir?
Yes.
Now I can write the numerator again using conditional probability is D given A into probability of A.
Yes. Okay.
I already know my D is probability of D given A into probability of A plus probability of D given B into probability of B plus probability of D given C into probability of C. This is what I know already from law of total probability.
Yes.
So this is my probability of A given D. Is that clear?
Yes, ma'am. Yes. Thanks. Yes, thank you.
Now let's end this small game. Okay, this is what is referred to as the Monty Hall problem. Is this clear? This Bayes theorem and Bayes probability thing.
Yes, ma'am.
Yes, ma'am.
And this is the Bayes theorem. Yeah.
Ma'am, I just have a small question about this Bayes theorem. So, ma'am, the similarity between Bayes theorem and law of total probability, I got it totally. But the thing is, my question is, when we are calculating the law of total probability, that means we are just trying to find a small part, I mean, let's say you gave the example of the defective items. So we just categorize the defective items totally. So that's why its law of total probability is used. But when we are just so ma'am, when we are using Bayes theorem, so that means we are categorizing, like we are specifically want to know like from which section or which part we are actually want to like know, like the
Exactly,
defective
that's
part is
what I
coming.
want. Yeah, so what the Bayes theorem basically does, let me go back to this example. Okay, let me try and go back to this example. See, initially what we had was, so let's go back to this example. I have products coming from 3 factories, okay, A, B, and C. Is it clear?
Yes, ma'am. Yes.
Okay, now what is the chance that it comes from A? 30%?
30%, yeah.
So imagine that I don't know whether it is defective or not. I have these 100 products lying with me. I pick up a product and I am asking the question, what is the chance that this comes from A? And you say it is 0.3. Agreed?
Yes. Yes, ma'am.
Okay. Now I'm giving you an extra information. And that is, I'm giving you an information that that product is defective.
Okay.
Okay, now what is the chance it would have come from A? That is the formula I have written. I have not computed it, but that's a formula.
Yes, ma'am.
Okay, so what is happening is I'm giving you some extra information. And that is making you revise whatever estimate you had earlier, right?
Yes, ma'am.
Probability of A was 30% was without this information of it is a defective. Now I'm giving you that extra information that it is a defective. So I'm asking you what is the chance that it comes from A? Given this extra information, it is defective. Is it clear?
Oh, okay, ma'am. Okay. Now I totally got
Now
it.
you have what was prior and now what is posterior. Prior is without this extra information. Now A given day is the posterior information. Is it clear now?
Yes, ma'am. Yes, ma'am. Thank you.
Right? Okay. Now suppose this whatever information is not affecting it, posterior and the prior would be the same. Get it?
Oh, yeah, ma'am. Yes, ma'am.
But now in this case, it was not the same. Is it clear?
Okay. Yes, ma'am.
Yeah. Okay. Yeah, I will give this teaching PDF. This PDF has everything which was there in the earlier PDFs, but I have absolutely no problem in sharing this PDF. But let's look at one nice example. Just give me a minute. I'll pull it out. Are you all able to see the screen?
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Yes.
So this problem is called the Monty Hall problem. Okay, it's a game show. So imagine that you are all participating in this game show. Okay. Now behind one of these doors is a very expensive item. So let's assume that there is a car. Okay, and there are inexpensive items. There are boards behind the contestant. Suppose you are a contestant and you are asked to choose one door. Suppose you choose door 1. Okay. And the game host is going to open one of the remaining 2 doors. Assume the game host opens door 2 and shows you a goat behind it. The game host is always going to open a door which has a goat behind it, right? Now the contestant is given a chance to change his initial choice. Okay, so if you are door 1 and the host is showing you door 2, you have a chance to change your initial choice. The problem is whether or not the contestant should change his or her initial choice. Is the question clear?
Yes, ma'am.
Yes, ma'am.
Ma'am,
If you were the contestant, would you change your choice?
ma'am, after choosing the door, is the products behind the door shuffled also?
No, nothing is shuffled. You're not open suppose you choose door 1, the host will open a door and show you a goat. Okay. Now the question is, will you change your choice or would you stick on to the choice of door 1?
Change, will change.
Do not change. I will not change.
You'll
Because
not change. Why?
Because I will have the probability of 50% because there should be car also.
No, if what is the chance of a car being there? How many would change and how? So this is the famous Monty Hall problem. You all can Google it and you all can solve it using the Bayes theorem. Okay, that would be for your weekend. You can all, this is called the Monty Hall problem. And you can see that if you change your choice. So now what, so without even going to show it, now if I show you it's a goat, that is an extra information I'm giving you. What is it? So what is the, without, when you're beginning the game, what is the chance of finding a car behind every door?
1/3.
1/3.
33%.
1/3. Okay. Now I am showing you one of the doors and it's a goat. Okay. Now the thing is, given this information, what is the chance of you finding a car behind a door? Behind the first door?
1 by 2.
1 by 2.
50%, because we know that
Behind the
other
third
door-
door be higher than the first door. Okay. Behind the third door would be higher. So this is what it is. You are asked to choose a door. You choose a door, you stick, you get a goat. Okay, you change, you get a car. You choose a door, you stick, you get a goat. You change, you get a car. You stick, you get a car. You change, you get a goat. So how many, what is the chance of you getting a car now?
2 by 3.
66.67%.
2 by 3.
Changing better when you get change. What is the chance of you getting a car?
2 by 3.
2 by 3.
Yes, so now you can, so this, so would you change or would you stick on?
Change.
Change.
So now apply Bayes theorem and prove that your probability of changing is higher than you sticking on. Is that question clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. You can say that, yeah. So the people who said that they change would always get, you'll not get a car. Your chance of you getting a car is higher. Okay. Because if you change, you'll get a goat also, but that chance is lesser, right? If you choose a car and you get a car, if you stick, if you change, you could get a goat also, but the chance of you getting a car is higher than the chance you get a goat when you stick. Is that clear? Okay. So you can,
Ma'am, just one question, ma'am. Sorry. When you say, when you in the first choose, your probability was 33% of getting the car.
Yeah.
When you choose second time, there is a 50% probability that you will get a car, right?
pardon? No, that depends on, see, that's why I'm saying that is a conditional probability. So this conditional probability, I have put it in terms of a tree. So what is the first thing? You choose a door, this blue thing, you have a 1/3 chance of a car behind it. Is that clear? The blue.
Yes.
Right?
Yes.
What about the pink? The pink is getting a car once you change. What is the chance of you getting a car here?
2 by 3.
2 by 3. What is the chance? So that, would you change or would you retain with your original chance? This one?
Change.
That's it. Okay, so you can apply the laws and do it. But this is easily understood through a tree. Is it clear?
Yes,
Yes.
ma'am. Actually,
Yes, ma'am.
actually, it is based on the concept that there is one solution, but there are many wrong solutions. So if a random person choose a solution and stick, then most probably he will stick to wrong solution.
Okay, right.
Ma'am, I have one question here.
Yeah.
Ma'am, when you choose a door with a goat behind it, that option is completely blocked, right?
Which option is completely blocked?
So we have two goats behind the doors. So when I select one door, the other door with a goat a goat behind it is open.
Door. If you choose a door with a goat, okay, the host will open only this door, right?
Yeah.
Suppose you choose door 1.
Yeah.
Okay, and it has a goat behind it.
Yeah.
Will the host open this door and show it to you? The third door?
No.
The hostess are going to open only this door.
Yes, ma'am. But then.
So if you change, you'll get a.
No, that options are completely blocked. No, I will not choose it. No, once the host opens that door.
Yeah, that's why your conditional probabilities would change. I just depicted as a diagram. This you can write and see. This is probability of finding a car behind door 1, door 2, door 3. These are my prior probabilities. Okay. What is the chance of you find a car given that there's a goat behind it? With the door, the host opens a door. That way you can write it as finding a conditional probability in terms of formula also. This is just through a tree. Is that clear?
Yes,
ma'am. Yes, ma'am.
Okay.
Yes, ma'am.
You can write this. So what is the next thing which I'm going to do is the notion of probability trees. Okay. Now what is a probability tree? I can represent this outcome of a random experiment using a tree structure. So you can see that when I toss a coin and I have only head and tail, I can just represent it as a head and tail, each with equal probability. When I toss a coin twice, you can see that in the first toss, I have a head. In the second toss, I have a head and tail. I can compute the probabilities as probability of head into probability of head, which would be 1 by 4, 1 by 4, 1 by 4, 1 by 4. Okay, this is how I can get it. Now, suppose I am picking a ball from 3 black and 4 white balls. Okay, the bag 1 has 4 white balls and 3 black balls. Okay, now what is the chance of finding a black ball from bag 1?
3 by 7.
3 by 7.
3 by 7. Okay, right. What is the chance of finding a white ball from bag 1?
4 by
7.
4 by 7. Okay, so if I find a white ball, I'm going to add 2 balls of the other color. Okay, so in the bag 2, or let me make it much simpler. If there's a black ball, I pick it up from bag 2, which has 3 white and 6 black balls. If I pick up a white ball, I pick up a ball from the second bag, which is 4 white and 5 black balls. So what is now the chance of picking up a white ball from bag 2 in the first case? From here, from this bag.
3 by 9.
1 by 3.
3 by 9, right? From bag
3
2.
by 9.
3 by 9. From bag 2, bag 3, this is bag 3.
4 by 9.
4 by 9.
4
Okay.
by 9.
What is the chance of picking up a black ball from here?
6 by 9.
6 by 9.
What is the chance of picking up a black ball? It is
5 by 9.
5 by 9.
So after the end of this, what are my possible chances? I could have either 2 black balls or a black ball and a white ball and a black ball and a black ball and a white ball. Is that right? So I can
Yes,
just
ma'am.
multiply the probabilities across my edges, which is 3 by 7 into 6 by 9, 3 by 7 into 3 by 9, 4 by 7 into 4 by 9, and 4 by 7 into 4 by 9. And you can verify that this would add up to 1. Is that clear?
Yes, ma'am.
Yes,
ma'am.
Okay. So that way you can use.
Yes, ma'am.
Okay, so this way, now you can use this logic. What is the chance of me finding a black ball given the first ball was a black ball? What is the chance of me picking up a black ball in the second, this one, given the first ball was a black ball?
3 by 7 into 6
by
by
7
9.
into 6 by 9.
Is the same as picking the black ball from the second bag?
Is it the same?
Yes, ma'am.
No, second plus
6 by 9.
It's going to be 6 by 9, right? That was right? Because it is probability of B1 intersection B2 divided by P1, which is going to be 6 by 9, right? Agreed?
Yes, ma'am.
Yes, ma'am.
What is the chance of you picking up? So this is what, so if you look at the way we have computed this, this is nothing but probability of B into probability of B2 given B1 is 6 by 9. Probability of B2 given W1 is 5 by 9. They are not same, right? The chance of you picking up a black ball in the second draw depends on whether it was a black ball or a white ball in the first draw.
Yes,
Yes,
it
ma'am.
depends.
So they are
Yes, ma'am.
dependent. So you can see that the probabilities are different similarly for a white ball.
Yes.
Yes, ma'am.
Yes,
If it was not this case, then after that would have
it would have same, ma'am. Like,
it would have been the same. For example, here, the chance of you getting a head in the second toss, whether it was a head or tail in the first toss, is the same, 0.5, 0.5. Similarly, the chance of you getting a tail in the second toss, whether you had a head or tail in the first toss, is the same, right? 0.5, 0.5. Is that clear?
yes,
ma'am.
ma'am.
So
Yes,
here,
ma'am.
my second toss, getting a head or tail, is independent of the outcome of my first toss, whereas here, the outcome in the second toss depends on what was the outcome in the first toss. Is that clear? Again,
Yes, ma'am.
independence and how you can
Yes, ma'am.
capture it using a probability tree. Probability trees are very, and this is what I showed even for the Hall problem. Through a tree, I just wrote down, but you can compute the probabilities and you can find for yourself that always when you make a change, it will be more useful. Okay?
Ma'am,
Yeah.
ma'am, how to solve questions regarding where the ball is transferred from one bag to another bag?
Pardon?
There are questions where ball is transferred from one
Yeah,
bag to
that's not the
another
same
bag.
way, right? So suppose here, I say that, suppose I give you the same thing. I start with a bag of 4 white and 3 black balls. Okay. Right. If it is a black ball, I say that you are going to add a ball of the other color and don't replace this ball. So how many balls will I have at the end of this? If I find a black ball, I'm going to add a ball of the other color. So what is the other color? If I see a black ball, what is the ball I'm going to replace it?
White color.
White
So how
color.
many white balls will I have?
5.
5.
5 white balls, and I'll have only 2 black balls because I'm not black ball, right?
Yeah, we are
And if
replacing
the
it.
white ball, I'm going to replace it with the ball of the other color. So what would I have?
4 and 3, like 4 black and
3
3
white
white.
and 4 black, right?
Yes, ma'am.
So again, I can compute it that way. That's what I said. If you start drawing these trees, it will be very easy for you to understand. That is very similar to I'm transferring from. Is it clear?
Yes, ma'am. It's quite
Yes,
clear now.
ma'am.
Yeah. Yeah, so you write down the tree, right? I have box A, box B. Just the ball is chosen from A and it's placed in B. Draw the tree and you can find out, okay, how to do it. Right? Okay, I think it is time. I hope this session was useful to you all.
Ma'am, last one question, ma'am.
Yeah.
Will you please define independent and dependent events in simple words?
It has been defined, I think.
I do not know how to make it. See, dependent is, again, let's go back here. Let me use this example to defend. I'm tossing a coin twice, okay? Is that clear?
Yes, ma'am.
Right. So this, whatever outcome I have here is the outcome of my first toss.
No, it's not sharing, madam.
Huh? I'm not
The
sharing.
screen is not shared.
One second. I'm sorry about it.
Screen is not shared.
Yeah, I'm sharing. I'll share it. Right. Can you see it now?
Yes, ma'am.
Okay, this is my first toss, which is, what are the possible outcomes? A head in my first toss or a tail in my first toss, and it can happen with probability 0.5, 0.5. Okay. Now I'm tossing the coin for the second time. You tell me, without any knowledge of probability at all, whether you're going to get a head or tail in the second toss. Does it depend on whether you got a head or tail in the first toss?
No, ma'am.
It is independent, right?
Yes, ma'am.
Right. Right. Now let's look at this. Now, whether you're getting a, so I am here, I'm doing the same thing, but I am picking up balls. Okay. If I get a black ball in my first, so imagine that I have, so this is a loaded, so you can think of this as a loaded coin where the chance of getting a head is higher than the chance of getting a tail because it is 4 by 7 and 3 by 7. Okay. Right.
Yes, ma'am.
Now, if you get a black, you are going to go to bag 2 and pick up a ball again. If you get a white, you are going to go to this bag 3 and pick up a ball again. Now, the chance of you getting a black ball in the second time, does it depend on whether you picked up a black or a white ball earlier?
Yes, ma'am.
Yes, ma'am.
Now, did you get the thing? So, this is the same thing as I can look at it as HH, HT, TH, TT, but with different probabilities where they are dependent on each other.
Yes, ma'am. I understand.
Huh? Whereas this is independent, right? This is dependent. That's all. Is it clear?
Clear, ma'am. Thank you.
Yes, ma'am.
Okay.
Ma'am, is it a printing mistake, ma'am? Back 2 instead of
Yeah, that is bag 3. You can take it as bag 3. Don't worry. Okay. Right. Okay. Okay, then. Thank you all. I think there's no more questions.
Thank you, ma'am.
Thank you, ma'am.
Thank you,
Thank
Thank
you
you
so
very
very
much, ma'am.
Thank you very much.
Thank you, ma'am.
Thanks for the great session, ma'am.
Thank you so much.
Thank you, ma'am.
Ma'am,
Thank you.
one last thing, if I'm allowed. Ma'am, there was a single doubt. If this session is not strictly to week 7 and 8, I had a very small doubt from week 5 and 6.
I don't remember what was on week 5 and 6. You need to
Ma'am,
tell
it
me
was
about
about permutation and combinations.
Okay.
Permutation
Yeah.
and combination.
Right.
So,
Okay.
ma'am, it's just that there was one problem about the concentric circle arrangements where people have to be arranged in circles.
Okay, see, the one thing is I don't remember all the questions that are asked in assignments or practice assignments right
Got
away.
it.
Okay.
Got
Okay.
it.
And I think whenever there's a session,
Okay.
we can always use a discussion forum. I think Ishan, Prashant, all of them are here to help you guys there. Okay. And whenever they ask me to conduct a live session, I'm more than willing to do it. So you can do it and we can always have these sessions. Okay.
Got it, ma'am. Thanks a lot.
Okay. Thank you all. Good night. Thanks. I hope this was useful for you all. Okay.
Thank you, ma'am.
Thank you,
Thank you, ma'am. Good night.
Thank
night,
you,
ma'am.
ma'am.
Any extra
Good night.
Thank you, ma'am.
Good night. Good night, everyone. Thank you.
Thank you so much, ma'am. Good
Thank
night.
you. Thank you. Yeah.